All right, so what we're taking a look at here is the work energy theorem. What causes change in energy? In all cases, some force must act on an object, either giving it potential energy or accelerating it to have kinetic energy. A couple of definitions we're going to get through first here. The first one being mechanics, which is really just essentially it's a study of kinematics and dynamics. Kinematics and dynamics, study of how things move, and the study of motion itself. That's there. Now, involved in this is the mechanical energy, which really is just both the sum of kinetic energy and potential energy. All right, so if you take the potential energy and kinetic energy of the system at any one given point, that will get you the total mechanical energy. Really, there's only one formula here, which is dealing with work is equal to the change in energy. That the change in energy that we've got is due to the amount of work that is actually done. So a few associated things that we've taken a look at here. First of all, work is equal to force times the distance, or the overall displacement of the object in place, as well as the kinetic energy being 1/2 mv squared. So for example, if we take a look at an object that has moved from 2 meters per second east to 5 meters per second now traveling east, there would have had to have been some work done in order to accelerate it. The amount of work done can be calculated by its change in energy. The energy is just really the potential to do work, so the work done will be evidenced by the change in energy. Now, in this case here, if we're going from 2 to 5 meters per second, both going east, it's important for us to take a look here at what this means. First of all, we'll just choose a simple 2 kilogram mass, just as kind of an example to see how this works mathematically, that the work is equal to the change in energy. Taking a 2 kilogram mass, the energy that it had before this change can be calculated. So EK being 1/2 mv squared, 1/2 times 2 squared gets you a total kinetic energy of 4. So there were 4 joules of energy here, of kinetic energy, before the work happened. Afterwards, taking a look here, EK being equal to 1/2 mv squared. If we take a look here at this, 1/2 times 2 times 5 squared gets you 25 joules, meaning a difference of 21 joules. All right. It is important for us to remember that delta V squared is not equal to the change in final velocity minus the change in initial velocity. That is, in fact, it is the delta V squared. And the reason for this is because sometimes you might be tempted to factor this. We'll take a look at that exact same example here with looking at it both ways, just so you can kind of see what is going on with that. Just scroll down a little bit. All right, so again, going from 2 meters per second east to 5 meters per second east. This is, again, a 2 kilogram object, just for the sake of argument. Now, because work is equal to delta E. You could look at this as just saying it's 1/2 mv squared, where this would be the final amount, minus 1/2 mv squared, where this would be the initial amount. And we can factor this to get 1/2 m, and we've got Vf squared minus Vi squared. A lot of times people are tempted just to subtract the Vf from the Vi and then square it. But that is not the case of what's actually happening, right? The proper way to do this would be, again, 1/2 times 2 times 2 squared, 5 squared minus 2 squared. Gets you a total of 21 joules, as we saw before. However, if we were to take that 1/2 m Vf minus Vi and square it all, that would get you 1/2 times 2 times 5 minus 3 all squared. Well, that gets you 4 joules. We don't want to do that. It's not the right answer, and mathematically it is not what is going to be happening. Don't do it this way. You do want to do it this way. And so just remember that we're taking the final velocity squared and subtracting that initial velocity squared. Gets you that change in velocity squared that you might be tempted to look at. Okay, hopefully that is making sense. So taking a look here at a first example, an archer exerts an average horizontal force of 55 newtons on her bow and arrow system by pulling the string back 0.35 meters. If the mass of the bow is also, well, I shouldn't say also, 0.350 kilograms, what is the potential energy stored back in the bow? So what we've got here is this archer pulling back the bow, right? So this force here is 55.0 newtons, and the string is going back a distance of 0.350 meters. We also know it's 0.0350 kilograms. In order for us to figure out the potential energy stored in this system, well, again, work is going to get you the change in energy. And this is really just going to work the opposite of that first little bit that I was talking about in terms of the going from 2 to 5 meters per second. But we're looking at a change in potential energy. Assuming we started with 0 joules, so the energy before, this would be potential energy before, is 0 joules. The potential energy after, we can calculate by finding the force that is being applied through that distance. In other words, it is the actual amount of work that has been done. So instead of saying EP prime, it's probably better for us to actually take a look at this and call it W, the work being done, which will get us the potential energy afterwards. And that change in energy from 0 to how much work is done will get us the amount of potential energy afterwards. So we're really just multiplying 55 by 0.35. And so we're going to take that, we're going to type that into our calculators. 55 times 0.35. So 55.0 multiplied by 0.350. The amount of work being done is 19.25 joules, which will get you the potential energy in the system. Okay. So if we take a look at this fact that this now has a potential energy of 19.25 joules. We want to know what the horizontal velocity of the, that shouldn't say the bow, that should say the arrow. If the string imposes a 55 Newton force, 0.35 in the opposite direction once released. Well, this potential energy is really just being converted into kinetic energy. And so all that energy, that change in energy, is going to be going back into kinetic energy. That is going to be the amount of work that is being done. This is going to apply 19.25 joules of work to that arrow. So, moving along here, work is equal to the change in energy. That change in energy is 19.25 joules. Right? We know the work is being that force through a distance, 19.25 joules. This is going to be mass times acceleration using Newton's second law in order to get the acceleration of this object. We know the mass and we know the distance. This is a 0.350 mass, acceleration 0.350 meters, gets you the 19.25 joules. So first thing we're really doing here is we're finding the acceleration of this arrow. And we find that the acceleration is 157 meters per second squared. And that's just simply dividing both sides by the 0.35 and 0.35 again for the mass and the displacement. Assuming an initial velocity of 0, we're looking for the final velocity, and we know that this distance is 0.350 meters, right? That is the distance that this string is pushing back on the arrow. And so we're going to use the VF squared is equal to VI squared plus 2AD. We don't need to worry about the initial velocity because it is 0. And so VF squared is going to be getting us 2 times that 157 multiplied by the 0.350. Gets us the velocity squared times 2 times 0.35. Gets you a total of 110 meters squared per second squared. And so a final velocity will be square rooting this, gets you 10.4 meters per second. All right, I will be doing the second example with you here in a moment. Right now, there's another video. I will link it to the notes below for you to take a look through. And part 2 will be also linked in the notes below so that you can move on and see the last example here before we finish off this lesson.